We gotta remember that.
Okay, sorry about that with those exams. But I almost didn't bring them, but I thought I thought I should. I did curve the test. The mean after the curve was a 75, so there was some really, really good grades and some not so and some really not so good grades. I was a little surprised at how much difficulty some of you had with the electron configurations. Normally that's something students kind of learn easily, but maybe you just didn't look at it. Anyway, the stuff we're doing today is on the final, and also the stuff we're doing Thursday. So, try to pay attention. I know it's the end of the semester and you've a lot of workload and stuff, but we do have to push on. And yes, the final, yes. The final is December 14th at 10 a.m. in this room. Yeah. Don't worry. You'll know what's on it. The stuff I'm doing today is actually, since it wasn't on the last exam, it will definitely be on it. And you will have to do some, Sabine, you have to give me back the test because someone hasn't taken it yet. So look at it and give it back, okay? You don't have to put it back in the folder. You could just stick it on my, whatever you want. If you're just coming in, come and take a quick look at your test. I can't let you keep it because someone in the class has COVID and I'm giving the exam to her on Thursday. So I'll give them back permanently Thursday. But yeah, just take a quick look. I'm sorry about that. And then I think I'm gonna scoop them up because it's just gonna interrupt class. Hi, just taking a look at the exam. Giving it back. If you want to look at it further, you can look at it after class. All right. Okay. So we're finishing up with chapter 7. I was talking about the polarity of molecules. And when you determine if a molecule is polar, what it starts with is whether the molecule has bonds, one or more bonds that are polar. If a molecule doesn't have a polar bond, it can't be polar. So we first need to determine whether the bonds are polar. So we know how to do that already. So for example, I actually did this last time, an OH bond. If you look at the electronegativity values, which I'm writing down here, you see that there's a difference in electronegativity of 1.4. It's greater for oxygen, so that we draw an arrow pointing from the slight positive end to the slight negative end. That delta means slight, small. And so this is polar. Why? Because we have a cutoff. It has to be 0.5 or greater for a bond to be polar. And that actually, bond polarity was on the test. It was one question on it only. Okay, so then So that's a good example. The other one is a good example of CH. The electronegativity of carbon 2.5, hydrogen 2.1. The difference in electronegativity is 0.4. It doesn't make the cut. It's considered not polar. And this is where I differ from the book. So my cutoff, it has to be 0.5 to be polar. You shouldn't go around thinking CH bonds are polar. That's not true. So anyway, polar molecule. So for a molecule to be polar, it must have one or more polar bonds. So for a molecule to be polar, it needs at least one bond that is polar. And I think I did this example last time. Here's H2O. If you draw it with its bent angle that we know it has, and then you look at CO2, a little more space here. And then we look at CO2. Here's the Lewis structure. Okay. And I already talked about how there's a delta negative on the oxygen and delta positive on the hydrogens. And there's this dipole, this arrow that represents the charge difference between the two ends of this bond. Okay. And it points, the arrows point to the delta negative end. So we have these two arrows here. Now in carbon dioxide, if you think about whether that bond is polar or not, the electronegativity of oxygen is 3.5, carbon is 2.5. That's 1, right? The delta En is equal to 1 for both of these. So we have two dipoles. We have delta negatives on the oxygen and delta positive on the carbon. Now, the thing is, they both have polar bonds. But only H2O is polar, is a polar molecule. And why is that? We talked about this last time. Yeah, these two arrows, if you notice, the dipoles point in opposite directions. Completely in opposite directions. And the strength of the dipole, which is how different the electronegativity is, the strength of that dipole is the same in both directions. So the dipoles cancel here. Whereas here, we have one arrow pointing up and to the right. So this arrow is up and to the right. This one's up and to the left. Wait, no, this, yeah, left. This is up and right. And these arrows, okay, they're both pointing the same amount to the right or left. So it's like the side to side part of these arrows cancels, and they're both pointing up. Now, I know, we don't want to start learning about vector addition here or anything, but really, I'm not, I think most of you can see that the right part of that arrow and the left part of this arrow are the same. So they cancel. But why that is because you could think about this as being a component in both of these directions. So the component that points right, left, this part cancels, but then you have a net dipole, which is, this would be over here. This would be a net dipole. Those of you who had lab on Tuesday, did you see that dipole for the H2O? Wasn't that part of the lab? What was the lab about? Wasn't it about, oh, right. That's what I said. People who had, oh, today is Tuesday, duh. Well, you'll see that in lab today. All right. So anyway, so we can have situations like this, where the arrows don't completely cancel, but the right-left aspect might cancel. So water is a polar molecule because both of these arrows point up. So the net dipole in water is pointing this way. And net just means after you take into account both arrows, after you sort of add them up sort of in your head. Now, another way you could think about this is to do something we call vector addition. So if you have a vector like this and a vector like this, and a vector is just an arrow. It's got a direction and it's got a length. The length is like the magnitude of the dipole. So one thing you could do is if you want to add these two up, you could translate this guy over to this arrow over here. So you would kind of move it so that it goes, and they both start at the same point. No, sorry. So that you translate this one to the head of the other one. So I've just moved this arrow over here. And the net direction, you start at the beginning of the first one and go to the end of the second one. And you could see that it moves up. So if you prefer that, that's fine. But that's a little hard to picture for tetrahedral. So I don't recommend it. All right. So that's why CO2 is polar and CO2 is not polar and H2O is polar. So we have this handout here that I gave you that has basically all the situations that you're going to run into. So if you don't like the vector addition or trying to figure that out in your head, this piece of paper gives you almost all of the combinations that you'd ever have to worry about. So we have HCl here. Okay, so let's think about HCl. That's the first one. Here's the HCl on the upper left. And you could see it does have a dipole, but let's see why. Okay, so for HCl, if we look at the electronegativity, that's 2.1 for hydrogen and 3.0 for Cl. So that means chlorine is more electronegative. It pulls electron density towards itself, becoming delta negative. This is pretty easy. You have only one polar bond. There is nothing to cancel it. So this molecule is definitely polar. Oh, where is that? Huh? That's in the back of the chapter 7. It's in the sort of towards the end. Not this one. The one I gave out before has that. Okay. All right. We already did H2O. So here we have H2O. Here's the H's and the O. And you can see that you have this net dipole, which they call the overall dipole moment, that points up. So the side to side cancel. So this is, of course, polar. In CO2, even though we have two nice dipoles, they point in opposite directions. So CO2 is not polar, even though it has polar bonds. The bonds cancel, or the dipoles cancel, which brings us to NH3. So let's see, I have NH3 over here. So NH3 is a little pyramid, it's got a nitrogen on top and it's got these hydrogens in a trigonal but pyramidal, right? Because they're not in a plane with the nitrogen. It's not trigonal planar, it's trigonal pyramidal. So it's this little pyramid and all of the dipoles point up because nitrogen has an electronegativity of 3. Whereas the hydrogens are 2.1. So they're all pointing from the hydrogen to the nitrogen. And here's the thing. They're all pointing towards the nitrogen, which from our view here is up. Okay. And they have different side-to-side components. But when you have a trigonal pyramidal, like this is, primal, pyramidal, when you have a trigonal pyramidal structure with 3 equivalent dipoles, like we do here, the side to side cancels. It's not that the H's are canceling, it's that the component that has the angle here, you have a component up and a component to the side, and you have that for all three. And I really am not enough of an artist to show you in 3D how these arrows are going to cancel. But what you can clearly see is that the up component of each of these arrows is not going to cancel. They're all pointing up. Okay, so the net dipole points up towards, so it points up towards the nitrogen. So when you have an arrangement like this, a little pyramid, and you got three equivalent dipoles, you have a net dipole. So this molecule is polar, and the net dipole is pointing up. Now, what if one of these H's was something else? Well, then they're not going to cancel the side to side. So you'd have a different dipole, but you would still have those, but you would basically also have a polar molecule. There's no way they're going to cancel completely here. That's just impossible because they're not pointing in exactly opposite directions. Because you have this up component on all of them. I hope you can see that. I don't know. What do you think? Juliana, what do you think about that? Yeah, because they're pointing downward, right? But they're all evenly distributed. So which way would the side to side end up pointing? It doesn't make sense that there's even going to be a side to side component, and there isn't. They all cancel the side to side, and the net dipole is up. If you had to pick a direction that the side to side would end up being, there's no preferred direction. These things are pointing equally in all directions. So there is no side to side component. So anyway, we have a net dipole that points up towards the nitrogen. Okay, the next one I want to talk about, this is an unusual situation because we have only, remember, this is boron, and boron can accommodate 6 electrons very nicely and be satisfied. So if you had BF3, you would have very strong dipoles in each one of these bonds. Because fluorine has an electronegativity of 4.0 and boron is 2.0. That's actually considered ionic in the table, but I still say it's just very, very polar. So you have these 3 dipoles, big dipoles, pointing in these 3 different directions. So what do you think is going to be the case here? Well, I have the answer written here. Yeah, so when you have a trigonal planar arrangement with 3 equivalent dipoles, they cancel. Here, actually, you can show this pretty easily by using vector addition, but I'm just going to show this to some people. Maybe some people are interested in this. Oh, I drew that one a little too long. So if you wanted to add up vectors 1 and 2 here, you would take 2, and what you do is you move the tail of the arrow to the head of the other arrow. So you translate it, and then you draw an arrow from the beginning to the end. And you could sort of see, it's not that great a drawing, that this arrow and this arrow will now cancel because they're pointing in equal and opposite directions. So if you don't like that, fine. Just know that when you have a trigonal planar molecule with 3 equivalent dipoles, they cancel. And this is a nonpolar molecule. Now, if you had, let's say you had boron with a hydrogen and 2 fluorines, what do you think about that? Would this be polar? You don't have 3 equivalent dipoles. Hydrogen is 2.1, boron is 2.0. That's not even a polar, you only have 2 arrows now. What does that kind of look like? Remember water, where the side to side cancel, but you had a net direction? right? So the net dipole would be like that if you had BHF2. So there's a net dipole here that points down, or from the boron end to the hydrogen end. This would be delta negative and delta positive right there. Okay, so let's go on to the next one on the drawing there. Yeah,
How do you know if there's supposed to be an arrow? Like,
if you have a difference in electronegativity that's 0.5 or greater,
it goes,
it goes from the lower number to the higher number. Yeah, because it's pointing from plus to minus, from delta plus to delta minus. So there's 3 dipoles here, but these all cancel. But if I was to change one of them, then they would no longer cancel. Yeah. Okay. So on the chart, the next one, so we did this one, we did these, we did this, we did this. So now we have CCl4 and CH3Cl, and I'm also going to do CH2Cl2. So these are tetrahedral arrangements, right? We have 4 groups of electrons on the central atom. This is tetrahedral electron geometry, and also tetrahedral molecular geometry, or shape, or structure. So, and you remember this isn't the best drawing. I mean, it's coming out and going back. That's what you have to remember. Okay, now, are there dipoles here? What is the electronegativity of carbon? It's 2.5. What is it for chlorine? It just makes it across the border of it has a big enough delta En to just be polar. So we have these 4 dipoles pointing in these 4 different directions of a tetrahedron. When you have 4 dipoles pointing in the 4 directions of in a tetrahedral compound, what do you think? What do you think? Is there going to be a net dipole here? No, it's almost like space is being divided into these different, very equally spaced regions, and you have these arrows pointing in these 4 different directions. If there was going to be a net dipole pointing in a certain direction, well, what direction would it be? It doesn't make any sense. There's like an even spreading of these arrows. So basically there is no net dipole. What does that mean? That means that you adding up all these dipoles gives you nothing. Gives no net dipole. So CCl4 is nonpolar. So when you have a tetrahedral structure like this, and you have 4 equivalent dipoles, they cancel. And remember, what you have to have for polarity is you have to have at least 1 polar bond, and you have to have a certain asymmetry so that the dipoles do not cancel. And that's what you have. And here you do not have that asymmetry. It's too symmetrical. So the dipoles cancel. But what if you had 3 hydrogens? So again, we have the same tetrahedral structure, but you have hydrogens here and a Cl here. So what about this one? What's that? 2.5, 3.0, 2.1. So we have no dipoles down here. And you only have 1 dipole. Well, there's nothing to cancel it. So this one is going to be polar. So it's a polar molecule. Now, what if I did this? So we know if we have all 4, they cancel. If we have 1, they don't cancel. What if you have 2? What if you have CH2Cl2? No, a non-polar can't cancel anything. There's no dipole here. So you have a dipole here and a dipole here. That's kind of like the H2O example where you have a net dipole in the middle like that. And you would have, this would be delta negative, delta positive, delta negative. What's that? Well, the side to side of these two arrows will cancel, but it will have a net pointing in that direction. So here, you'd have an arrow here and an arrow here, and you translate your arrow up, and you see that your net, you go from the beginning to the end of the second one, and you have a net dipole in that direction. I think you can sort of, you don't have to learn vector addition to see that this is going to be polar, because you have arrows pointing in these exclusive directions and nothing pointing in this direction, right, to cancel it. So it'll be about between the two arrows. Yeah.
Why there a polar?
Because, we put the cutoff somewhere. It's not enough of a difference. And if you did have a small, let's say you did have small dipoles there, they wouldn't be big enough to cancel those two, because those are stronger. Yeah. No, hydrogen will be bonded to oxygen, and then it's polar. Yeah. Yeah.
So
Yes, this is polar. Yes. Okay, so the case for tetrahedral, if you have 4 equivalent, non-polar. And if you have anything else with tetrahedral, if you have polar bonds, you will have some polarity, because they won't cancel. You have to have the 4 for the cancellation to happen. All right, I'm going to ask you at home to go back to activity 4. Now let's just take a look at it. A lot of them we sort of done as examples, but remember, this was activity 4. Let's see if I can get to it. Where is it? Yeah, it's these. Remember these blocks? So we did the top, but here I want you to go back, and I don't have time to do this in class. I wish I did. But you can go and look and see if you have calculate these electronegativity differences. If you want to hand it in, don't hand in these papers, because you need them to study from. So just copy this part onto another paper for each molecule, and I can give you credit for a special problem if you hand that in. Okay, so it's asking you to figure out if there's any polar bonds. If so, which do they cancel? And some of these we've done already, not this one. This is one we haven't, but we've done like CH3F. That's very similar to the one we did with CH3Cl. This is BF3. We did this one already, so it's just review. This one, you could see you don't have any dipoles here, but you do have a dipole, because this is 2.1 and 2.5 and 3.5. So you have a dipole there. Anyway, so I'd like you to do that on your own. Okay. I may have actually posted the solutions already to that activity, so it should be really easy. All right, so I have to start valence bond theory with you at this point. And this is pretty important, because when you get to organic chemistry, you need to kind of know this. It starts with this in a way, at least I know I'm pretty sure that's where it starts, but anyway. So I want to tell you some of the fundamentals of valence bond theory, and it has a big fancy name, but it's, and and there's some complications to it, but when it comes right down to actually using it, it boils down to something that's pretty visual and not that difficult to figure out. So bear with me and we'll get to that. And you'll be able to do some of these problems, I think, relatively easily in the end. So what it does is it considers the bonds it considers bonding to be between two atoms at a time. Okay. And actually I have you have a handout on this. This is the handout I gave out today. So this is what we're talking about here. I don't think so just as introduction, it handles bonds between two atoms at a time, as you might imagine. And that these bonds form from overlaps of orbitals, overlaps of atomic orbitals. You know what those atomic orbitals are. 1s, 2s, 2p are basically what we're going to be dealing with here. And so that's what we're going to be dealing with. And also 1s for hydrogen. I should put 1s there. Okay. So what I want to first do is have you look at this diagram. It's an interesting diagram. It's got energy here. And what I want you to focus on are these pictures here. Okay, so we have these two atoms that are far apart here. They're far apart. And I couldn't draw them really far apart, or they wouldn't fit on the diagram, but they're far enough apart here so that there is basically no interaction. In other words, they cannot feel that the other one is there. And that's what we call the zero of energy. So when they're far apart, notice this is zero here. So and this x-axis here is simply the HH distance. We're talking about two hydrogen atoms, all right? So when they're far apart, they're not feeling each other. There's really no energy associated with this interaction. They're just too far apart. But as they get closer together, so here now they're starting to get close together, and the energy is going down from zero. So the energy is getting lower because it's becoming more stable. Why? Because the electrons from one of these atoms are becoming attracted to the nucleus of another. So you start to get this electron nuclear attraction between the two atoms. And so start at the beginning, it's kind of a weak attraction because they're too far apart. As they get closer, you get a stronger electron nuclear attraction until you hit this minimum point. So here's where you have the strongest electron nuclear attraction. And at this distance, this is what we call the bond length. Because of course, those two atoms are going to be as far apart as they need to be to have the strongest stabilizing interaction. Okay. Now, why, when you put them even closer together, does the energy go up like this so fast? So remember what's on the x-axis here. It's the distance apart. So we're looking at what happens to this energy as you get closer and closer together. So why do you think the energy is going up here? What is another interaction that you have when you have two atoms? It's not just attractions for the electrons on one and the nucleus on the other. When you start to get closer together, the two nuclei start to be close enough to interact with each other. And what type of interaction is it going to be between two nuclei, right? That's repulsive. That's going to make it less stable. So this goes up whoosh really fast because of nuclear repulsion. So I always say that this is like the happy place here, where the stabilizing interactions between electrons and the nuclei are greatest. And what you have to remember when you have a bond is that you have a region, like so we have, say we have these two atoms, they come together, they form a bond, they overlap. For hydrogens, these would both be 1s orbitals. So they overlap when they come together. And what was I going to say? And, oh yeah, here it is. The electrons in this overlap region are attracted to both nuclei. Which is why a bond stabilizes, which is why when you have two atoms bonded together, you have a lower energy than two separated atoms. It's because those electrons, when they're in the overlap region, they're attracted to both nuclei, which this is the reason for the greater stability of bonded atoms. Okay, so another way to draw this little picture here is to just kind of put it together and have this region of overlap. Okay, so that's another way to think about that's a way to think about it. It's just kind of like that the electron cloud is now encompassing both of those nuclei. Okay, so some of these ideas that are written down here I've already said. Bonds are considered between pairs of atoms only, two at a time. The chemical bond results from overlap of atomic orbitals. So we have the overlap of the 1s's in this case, 1s and a 1s. Okay. Now, here's the other thing that I didn't mention, that each of these orbitals has to be half filled. So when you have a 1s, a hydrogen 1s, right? You have hydrogen 1s1 and another one. This is half filled. Why do I say that's half filled?
Shell is full.
Right, if that, well, it's not just the shell, it's just this S subshell. There's only one orbital. That orbital was filled, it would have two. So we have each one is half filled. That's the case here. That we check that off. Each is half filled. Okay. In the bond, there will be two electrons. So every bond is two electrons, and their spins will be paired in the bond. So I could redraw this kind of like this way, that you have two electrons in this bond, and I could kind of draw it like this. It's that where you have the two electrons kind of in that overlap region, and there's your two nuclei or something like that. Okay, so here your spins are paired. But that's kind of minor point. We really don't ever deal with that point, so it's not that important to us. Okay, there's some other points to think about for this valence bond theory. Of course, we know valence electrons are what are responsible for reactions. So when you're making bonds, only valence electrons are involved in the bonding. So you basically ignore the core. The core is not involved. Another thing is that the shape of the molecule is determined by which orbitals are involved in the bonding. So you have to have orbitals pointing in the right directions to get the bond angles right, to get the angles that we know that that molecule has. So the orbitals determine the bond angles. We'll do some more on that. And the strongest bonds are from overlap of orbitals that are pointing right at each other. So for example, if I had like a p orbital and another p orbital, that this sort of overlap is pretty good, but this kind of overlap is not as good. So notice here, this bond is trying to come into this other p orbital in a region where there isn't much to overlap with. So this is what I would call bad overlap. And this is good overlap. But anyway, these are, this is some of the, we won't run into too much of that. We have pretty simple overlaps between similar orbitals. All right, I do want to talk about what a sigma bond is. So this bond that I've been telling you about, the two hydrogens overlapping, there's the overlap region. And what I want to define here is something we call the internuclear axis. So here's two nuclei. This is the internuclear axis. I affectionately call it the internuke axis. And you could see that the overlap region is on this axis. When this is the case, we call this a sigma bond. That's a Greek letter S, is a sigma, okay? We can also, and we will have this, you will see this, is you can also have what we call a pi bond. That generally happens from overlap of p orbitals, or p-type orbitals. So here you have overlap. And this is the internuclear axis. So because you have the nucleus and the nucleus. And here you could see that the overlap is above and below the internuclear axis. And another way to draw this is the way I mostly draw it. So here would be the nuclear axis, internuclear axis. Usually you can't draw these close enough together to show that overlap because it's just too hard to do. So this is another way of showing that kind of overlap. So this is a pi bond. And this is just one pi bond. This is not two different bonds, top and bottom. This overlap top and bottom is one pi bond, okay? So overlap top and bottom is just one pi bond. And that's because the internuclear axis is over here, and you're above and below that axis. So that's a pi bond. So this would be a pi bond that happens from overlap of two 2p orbitals. So we call it pi 2p 2p. Okay, because those are the two orbitals involved. And this one, this sigma one, since these are both 1s's, this would be sigma 1s 1s. So we say which type of bond it is and which orbitals are involved in the bond. Okay, so I'm going to apply this to a relatively simple molecule, the molecule methane. All right, methane is CH4. Okay, and I'm going to tell you the problems that come up when we start to think about this, the bonding in this simple molecule. So let's talk about bonding in methane. Okay, so methane has hydrogens. Hydrogen has a configuration 1s1, and there's 4 of these. And then carbon has a configuration 1s2, 2s2, 2p2. Remember, carbon has 4 valence electrons. There they are, 2 plus 2. Those are the electrons in the last end shell that isn't filled. Okay, so there's 4 valence electrons. Okay, so if I draw my little block diagram, here's my 1s1 for each hydrogen. And for carbon, I have the 1s, the 2s, and then 3 2p's. There. Okay, so remember, if we go back to, the guidelines, we need to have half filled orbitals in order to form bonds. And if you look at, oh, look what I did. Wow, that's really funny. And if you look at this configuration of carbon, you notice that there are only two half-filled orbitals. So from the outset, that's pretty curious. It tends to imply that CH2, so is CH2, right? Because you can only have overlap with two hydrogen 1s's. Wait a minute, is CH2 the simplest hydrocarbon? But we know that's not true. We know it's CH4. Yes. It's 2s2, 2p2. It's the last end shell. Yeah, yeah. Okay. So we see we already have a problem here because we do have so here's the 3p orbitals, the 3 2p. This one goes in the back. It's hard to draw. Like kind of like that. Okay. You know, we have one half filled and another half filled. That's what is signifying here. And I can imagine, you know, having a hydrogen and another hydrogen. And here's a much nicer picture of it, right? Here you would have a hydrogen 1s approaching, and then you would have this half filled. Okay. But then you'd be making CH2. Can you even draw a Lewis structure for CH2? You would have 4 valence electrons here, 2 from that, you have 6. You don't even have anywhere to put those electrons. So this is just, this is not possible. We also know about the simplest hydrocarbon. We know that CH4 is the simplest hydrocarbon. And we know also, by the way, if you had this molecule, what would the bond angle be? It would be 90 degrees, right? Because you would have your carbon here and your hydrogen nuclei here. This would be 90 degrees. And we know that CH4 is the simplest hydrocarbon. We know that CH4 is tetrahedral and that it has a 109.5 degree bond angle. Okay. And we also know for CH4 from experiments that it has 4 equivalent CH bonds. Now, how are we going to get 4 equivalent CH bonds out of a situation where we only have 2 half-filled p orbitals? We really can't get CH4. So there's something flawed about the theory so far. Okay, so how are we going to get 4 equivalent CH bonds here? Well, what you need is you need to have 4 equivalent orbitals on carbon. We're going to need orbitals, 4 equivalent orbitals that sort of point like this. So that's the big, you know, we need 4 equivalent orbitals on carbon to get a molecule like CH4 to be the way we know it is. Okay, so let's think about carbon's orbitals. And I'm going to tell you the part of the theory that's the most unusual. So we have this electron configuration for carbon, but I'm going to draw a little energy diagram. Okay, we've seen that it's 1s2, 2s2, 2p2, like this. But I'm going to draw it on an energy diagram. So here's my 1s down here. Here's my 2s over here. And here's my 2p above it. And this is a very small energy difference. The 2s and the 2p don't have the same energy, but they're very close. Okay, so we have 2 in the 1s, 2 in the 2s, and then we have 2 in the 2p. So this is really just another way of looking at the box diagram. Does that make sense so far? Okay, I saw a nod head, good. All right, so now what we're gonna do, and this, we only have to do this for carbon, yeah. Well, that's what I'm gonna tell you. Yeah, I would be confused too at this point. Okay, so here's the energy. So what we do is we use a teeny bit of energy and we take and we promote one of these electrons up there. So we're going to promote one 2s electron to the 2p. So what we're going to end up with is this. So we still have 1s, 2s, 2p, but now we're taking, and the 1s we just leave alone, but we move one of these electrons up to the 2p. So now we have 4 half-filled orbitals. And it cost us a little energy, but we're going to get that energy back when the bonds form. Okay. We still have a problem though, because if you're expecting methane to have 4 equivalent orbitals to overlap with the 1s's on hydrogen, you're not going to get that from the overlap of a 2s, which is a spherical orbital, and 2p's, which look totally different. So what happens next is something that we call orbital hybridization. So we hybridize. What does it mean to make a hybrid? It means you're going to combine 2 different things and end up with something that's in between. That's what making a hybrid is, like genetically. You've got, 2 people with different characteristics, you come together, you have something that's in between for some characteristics. And you have the dominant recessive thing, which forget it, I don't want to get into that. But anyway, so what we do is we take a look at the CH4, we realize that we have 4 groups of electrons here. That tells us we need 4 equivalent orbitals, okay? And so what we do is we take these 4 orbitals that are different from each other. We take 1 2s and the 3 2p's, and we combine them to make 4. We call them sp3 hybrids. Why are they called sp3, you might ask? Because they are made, it's like s1p3. They're each 1 part s and 3 parts p. So these are sp3s. We no longer have a 2s or 2p's, but now we put these 4 electrons in these 4 hybrids. We still have the 1s, it doesn't change. Core electrons don't change. And now we have these 4 equivalent sp3 hybrids that we can use to overlap with the 4 hydrogen 1s orbitals. Okay. So what do these look like? So here I gave you this. You don't have the color version though, I'm sorry to say. But here we have 1 2s and 3 2p's, the 3 red orbitals. You combine them together and you get these sp3 hybrids. They're not really that accurately drawn here, but they end up having a large lobe and a smaller lobe. To simplify it, they put the nucleus in the middle, but the nucleus is actually over here. Kind of, that's what makes it more S-like, is that there's not a node at the nucleus. but all books draw it like this, and it's not really a big deal. The important thing, this is the only important thing, is that they point in the 4 different directions that are needed for 4 equivalent orbitals, so you will overlap with hydrogen, right, in these 4 different directions. So we call each of these an sp3 hybrid. When we form hybrid orbitals, you always, if you start off with 4 orbitals, you will end up with 4 orbitals. It's like orbital math. 1 plus 3, so 1 2s plus 3 2p's gives you 4 sp3s. Each of these is 1 part s and 3 parts p. And they point in those 4 different directions. So you have s. Oh, and by the way, when you draw these hybrids, you don't bother. We usually leave off this lobe. It just makes the drawing too complicated. We just draw the big lobe. So you go 1, 2, 3, 4. These are your 4 sp3 hybrids. And they each overlap with a hydrogen 1s. And that is your CH4 molecule. So if we go back to the diagram here, you could see that each one of these, each overlaps with a 1s on hydrogen to create 4 sigma bonds. Each is sigma sp3 1s. Okay, so let me draw that over here too. Actually, there's a nice picture I gave you right here. So here's your 4 sp3 hybrids. And now you have a sigma bond between sp3 and 1s. And you have 4 of them. Each of these is that. Oh, I already labeled that one. This one. I'll come back to that. And the nice thing is that now you have your 109.5 degree tetrahedral angle. Okay, so you have your 4 sigma bonds here. So that's CH4. Now, I have a piece of paper here. I guess it's activity 1. So this is just review of what we just did. You can take a look at it. What is the molecular geometry of methane? What is the molecular geometry of methane? I'm going to have you hand this in, I think. Oh, you have it on double-sided. Oh, we'll see if you get the other one. What is the molecular geometry of methane? How many groups are yeah, tetrahedral, right? So what does that make the HCH bond angle? 9.5, right? So basically this sheet is just a review of what we just did. And you can hand it in, I'll give you a special problem point for it. Okay. Activity 2 also. That's just review. Okay. So now we're kind of ready to do a slightly more complicated molecule. And you have this sheet as well. I think it's a handout I gave out last time. Oh, wait, I don't know if it's in here. Oh no, it's in this one, it's in the new one. On the 3rd page, you have this valence bond theory steps. Okay. And we're going to work our way through these for a simple molecule. And so the first thing we have to do, according to the steps, is to write the Lewis structure. And the molecule is C2H2 with a, sorry, C2H4. And this is the skeletal geometry. Okay, so skeletal structure. So first we have to draw the Lewis structure of that. And then what we're going to do is focus in on each one of the carbons and figure out how many groups of electrons there are on each of those carbons. So figure out the number of groups of electrons on the central atom. So basically we're considering two different central atoms. Okay, so we're going to find the number of electron groups. So how do we draw the Lewis structure for this? What is the valence electrons for carbon? Yep, it's 4. So how many total valence? We have 4 here, we have 4 here, and then we have, oops, 1, 1, 1, 1. So we have 8, 9, 10, 11, that's 12 valence electrons. So that's 6 pairs. So we start by drawing single bonds between the atoms. 1, 2, 3, 4. We've gotten rid of 4. 5, 6. Okay, but now we see, wait, what am I doing wrong? Yeah, 6. 1, 2, 3. Oh yeah, 5, 6. Yeah. So then we make a double bond. So we have C, double bond C. And now we can see that we have 3 groups of electrons on each of these carbons. Right? We have 1, 2, 3, or 1, 2, 3. So there's 3 groups of electrons on each carbon. So what is the geometry at each carbon then? So we've usually done this for when we have just one central atom, but in valence bond theory, we consider each of the atoms except hydrogen, and we count how many groups of electrons there are on each atom that isn't hydrogen. So that's what it says here. Figure out the number of groups. Oh, I thought it said it there. Well, it doesn't. I'm telling you, okay. All right, so we know because there are 3 groups that this is going to be a 120-degree angle, right? But we also know that we will need 3 equivalent hybrid orbitals. So whatever the number of groups on the atom is, this groups of electrons, just the way you counted up groups when we did the valence shell electron pair repulsion model, you count up the number of groups of electrons on each atom, that is going to be equal to the number of equivalent hybrids that will be needed. So how many equivalent hybrids am I going to need on carbon? On the first, let's call it carbon number 1. And it's going to needs 3, right? Equivalent hybrids. And the same for number 4. Number 2. Okay. So the next thing to do, if we go back to our list here, is to draw this energy diagram, just the way we did before. So we have carbon. Remember, here's energy. Here's the 1s. Here's the 2s. And here's the 2p. We have 2 in the 1s, 2 in the 2s, 2 in the 2p. Okay. Then we're going to hybridize. No, sorry, we're going to do the promoting the electron. For carbon, there's an extra step. We have to promote an electron because we need to get 4 half-filled orbitals. Okay, now we hybridize. Now, before we needed 4 equivalent hybrid orbitals. So we combined all 3 of the 2p's and the 1, 2s. But here we need 3. So we're going to take the 2s and only 2 of the 2p's. What do you think we're going to call those hybrids? They're going to have 1 part S and 2 parts P. So what do you think we're going to call them? 2. Yeah. So we'll have 3 sp2 hybrids. We'll still have the 1s, and then we'll still have this leftover 2p orbital. You'll see why it's left over in a minute. So here we have 2 electrons. Now we have 1 each in each of these. So here's our sp2 hybrids. Okay, and we're going to have the same on the second carbon. So let's take a look at this. First of all, let's take a look at sp2 hybrids and what they look like. So again, here we're combining 2 s orbitals and 2 p orbitals, 1 2s plus 2 2p's, and we're getting 3 sp2 hybrids. And they point in the direction you would expect, because we have 3 groups of electrons. We're going to need 3 hybrids. They're going to point in the direction of trigonal planar, right? So this is a trigonal planar set of orbitals. Each of these is an sp2 hybrid. So these are planar, and they have a 120-degree angle between them. Okay. So let's take a look at how they would, at how we can combine these orbitals. So here I had I'm just going to repeat this diagram. This is what we had our sp2 hybrids, 3 of them, and we had a 2p that's left over. And here's the 1s. These are all half filled and ready to overlap with something else. So this is carbon number 1. Well, all the carbons are the same here. The other one also has 3 groups of electrons. If we go back and look at the Lewis structure, these 2 carbons both have trigonal planar, both have 3 groups of electrons. They're both trigonal planar. Okay, so carbon number 1 and carbon number 2 basically give you the same energy diagram. So that's carbon number 1. Here's carbon number 2. So it's the same. We have 2 in the 1s. Then we have these sp2 hybrids, 3 of them that are half filled. Then we have a leftover 2p. Well, I say leftover, but why? You'll see now. Okay, now I'm going to tell you why. So remember, let's remember the Lewis structure that we had here. We had C double bond C, and we had H, 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 H. So this bond here, that's going to be from overlap of an sp2, right? sp2 on carbon. So this one will overlap with a hydrogen 1s. And 2 of these will overlap with hydrogen 1s. Okay, and the same is true here. So both of these overlap with hydrogen 1s, as you see, is necessary from the Lewis structure. Okay, so what about this guy and this guy? Well, that's going to be the first of the double bond. you're going to have overlap between those sp2 orbitals. So let me actually draw this out for you. These are the two carbon nuclei, okay? Let me make it a little further apart. And now I have my sp2, my sp2, and my sp2. All right, so these are all in a plane, just like it's a plane of this screen here. Each one of these are the two that are overlapping with the hydrogen 1s. On the other side, I have the same thing. Okay, so what type of bond is this? Remember, the nuclei are right there. Here's the other one, the hydrogen one. So the overlap is over here. So what type of bond is this? Is it sigma or pi? Remember, if it's along if it's on the internuclear axis, we call it a sigma bond. So this would be sigma. It's every bond has its own internuclear axis. It has to do with the atoms involved in that bond. So the internuclear axis here, this is the carbon nucleus, another carbon nucleus, but the hydrogen nucleus is over here. So this is the internuclear axis. We count this carbon nucleus on the left. We don't count the one on the right because our bond is between the left carbon and the hydrogen. This is the hydrogen nucleus. So we connect the carbon nucleus with the hydrogen nucleus of the bond, and we see that the overlap is on that axis. Every bond has its own internuclear axis, okay? So this is a sigma sp2 1s. It's from overlap of the sp2 hybrids of this one sp2 hybrid and this hydrogen 1s.
So right now you're asking only about the one hydrogen and the one.
That's right. I was asking about this bond right here.
Not the whole.
Well, I have to consider them one at a time. That's what valence bond theory does. It considers one pair of atoms at a time. Okay, so this is also, so now this is the hydrogen nucleus and the carbon nucleus, the internuclear axis. This also is overlap. That's along that internuclear axis. So that's also sigma sp2 1s. And of course, on this side, we also have sp2 orbitals. So this overlap, this is a sigma sp2 1s. And here again, sigma sp2 1s. I love when it does this to me. All right. So we had one leftover sigma orbital. One leftover sp2 orbital on each carbon. We still have the ones I circled in red. So that, see, you have this sp2 here and this sp2 on this carbon. And that's what these leftover orbitals, that's what these red ones are for. That's sigma, because the overlap is along this internuclear axis. That's sigma sp2, sp2. Okay? And we're almost done. So all of this is going on, what we say, going on in a plane. So we have our two carbons, we have our sp2, sp2, sp. This is all planar. These are 120-degree angles. Okay, we have our sp2s overlapping with hydrogens. But notice we have done nothing with this p orbital over here yet. And that is how you get a double bond. The second bond, the first bond of a double bond is a sigma bond from overlap of orbitals directly pointing at each other. Here they are sp2 orbitals. But then we have these leftover p orbitals. And where are they? I'm going to exaggerate it. they're pointing above and below the plane of the molecule. Because if you go back and you look at this hybridization thing, you have a 2px and a 2py. So if we're considering all this happening in the xy plane, the two orbitals that are in the xy plane were used to make the hybrids. The leftover p orbital is in the other direction, sticking out of that plane. And that's what we have here. And this overlap gives you your pi bond between the leftover two p orbitals. So, so that is the second bond, or I should say one bond of the double bond. But I think about this sigma as being the first bond of the double bond. And this is always what happens with double bonds. You always have a double bond. The second bond is from the overlap of leftover p orbitals that were not hybridized. Okay. So, so how do I draw this whole thing? I kind of did right there. But I have a nice picture of it. Let's see. Finish up with it. The anything from overlap of p orbitals will always be a pi bond, because they can only, because this is the internuclear axis here of the two carbons, that, and this is above and below that plane. So this is pi 2p 2p. So if you look at the sigma bonding, this is what you have. This doesn't include the pi bond. This is in a plane. I gave you this too. So you have these sp2 hybrids on each carbon. They overlap with two of the hydrogen 1s's on one of them, two on the other, and then they overlap in the middle. Two sp2s overlap to give a sigma bond. So this is sigma sp2 sp2. This is sigma sp2 1s. Same here. And it's equivalent on the other side. But what about the leftover two p's? So if you can imagine, you're looking down on this in a plane and you're looking down, and now you tilt it up. So you're looking at it from the side, right? So now you see these are coming out and going back. And here are your p orbitals. That this is just showing the overlap. It is what it is. Yeah, I did that on purpose. It's like I wrote the, this is the way it is. You get it. What other thing? Oh, you don't see that? All right, look, if you take this, all right, and you tilt it. So that you see these green lobs coming down, that now they're going to be coming out towards you. So those, so like this one and this one, it becomes this one and this one. Yeah. So now you're like, so because this is where you're looking from the top. So now you're going to tilt the whole thing and look at it from the side. So this guy that was going, down in this picture is now coming out forward in this picture. Yeah, that's really, that's one way that we show, yes, if you drew this close enough together to actually get overlap, the drawing would be so crowded that you wouldn't be able to see a thing. So they don't do it that way. They just draw it like this. But I'm not going to draw this fuzzy business in here, I'm not an artist, but some artist draws it like that. And that's really more like what it is, because it's spread out all over above and below the axis of the two carbons. Okay, but you could just think about it as two p orbitals. No, It's a good idea though, but I don't think so. I think it's pi because it's from P. And pi is just the Greek letter P. Yeah. Yeah. No, no, it would have an octet. It's still got each one. This whole bond here, that whole big red thing only has 2 electrons in it. This is not like 2 bonds. This is one pi bond. It just has 2 electrons in it. Notice they only show 2 of these things here. They don't have 2 on the bottom. Those electrons are all over the joint. They're not just on the top or just on the bottom. They're going, that's like quantum mechanics for you. They can be whatever they want to be, We only know the probability. Okay, so that is so let me make this a little simpler. So instead of drawing these orbitals, how about if I just draw the molecule like this? You have to know where it comes from. Okay, now we have carbons. They have 3 groups of electrons. They're going to be sp2 hybridized. This guy here is a sigma bond from overlap of sp2 and 1s. So is this. So are these. And then here is where we have a little bit of a complicated thing, right? We have a sigma from sp2 overlap. 1 on this carbon, 1 on that carbon. No, these are not electrons. And here, the second one is just a pi. Okay. And yeah, we could draw it. We could do a nice job drawing it like this. But I'm not going to ask you to do that. Yeah. Yeah. It takes a while to get to that. All right. All right. So. All right. Now let's do another molecule. We're going to do CH2 NH. This is activity 5. So it starts with drawing Lewis structures. So draw the Lewis structure of this molecule. I'll give you the skeletal. It has a C and an N, and then it has the 2 H's on this first carbon. And then it has 1 hydrogen on the second on the nitrogen. Yeah. Sorry, what can they only happen when? Yes, they only happen when you have a double bond or a triple bond. Yeah, if you have a double bond, you have 1 pi bond and 1 sigma bond. You always have 1 sigma bond, even when you have a single bond. If you have a double bond, it's going to be 1 pi and 1 sigma. If you have a triple bond, it's 2 pi's and a sigma. Yeah. Yeah, that's really fun to look at. All right. So how many electrons here? 4, 2, 5, and 1. 12. 6 pairs. Let's start with our single bonds. Okay, 5, 6. Are we happy with this? That's right. So we have to make an octet. So we have C double bond N. And now we have a bond to hydrogen, another one. And now we have a lone pair and another bond to hydrogen. Okay, now, how many groups of electrons on this carbon? No,
Three.
this counts as one. 1, 2, 3. So there's three groups. Double bond counts as one. So that's three groups of electrons. So that's, okay, then on the nitrogen, we have how many groups of electrons? Yes, yes. 3. So what is my geometry at this carbon with three groups of trigonal planar? And on this nitrogen, it's also trigonal planar. But now we also know something else. We know when you have three groups of electrons that you're going to have sp2 hybrids. Because they come from one 2s and two 2p's, and we know that orbitals add. When you have 1 plus 2, you end up with 3, and you need 3, so that's how you get 3, by 1 2s and two 2p's. So I'm just going to go over this again. This is for carbon. So 1s2, 2s2, 2p2. For carbon, we have to promote an electron. This is still 2p, 2s, and 1s. But we promote one of these. So we have now 3 half-filled orbitals. And now we're going to hybridize. So how many of these do I circle? To make an sp2, I circle 1s and 2p's. And I am going to make 3 sp2 hybrids. I put the energy in between that of the s and p, which is where it should be, because it's partial s, partial p. So that's my carbon. So you could see what's going on here. Because I'm only hybridizing 3 of them. If you have 3 groups of electrons, you need to hybridize 3. It's the whole 3 top ones, because then I'll have a half-filled 2s, which will not be equivalent. I have to have 3 equivalent orbitals, and I have to have a leftover 2p to make my double bond also. Because double bonds are, the second bond of a double bond, which is a pi orbital, is made from p orbitals. Yeah. Yeah. Okay, so that's carbon. So now let's do nitrogen. Nitrogen's a little different. There are also 3 groups of electrons on the nitrogen. So 3. That's how we know, Juliana. We have 3 groups of electrons will form 3 hybrids, so there'll be sp2. Same on nitrogen, right? We had 3 groups of electrons, but the nitrogen here is a little different, right? Because we have a different electron configuration. Nitrogen is 1s2, 2s2, 2p3, and those 3 end up in 3 separate orbitals, okay, by Hund's rule. So again, we have 3 groups of electrons. We're going to make sp2 hybrids because there are 3 sp2 hybrids. So we'll put these together and we'll make 3 sp2s. We still have 2 in the 1s. Notice what's different here is we have a pair in one of the sp2s. And take a look at the Lewis structure. Notice, let me just, you have a lone pair here on the nitrogen. That's going to be this lone pair that's in the sp2. This is going to be a lone pair, LP. Also, we have a leftover p orbital. That's going to be for our double bond. Notice we had a leftover 2p orbital here as well. Okay, so sorry. Yeah.
So when you promote the 2s, do you technically like kick out?
No, you put it into you put it in the empty one. You have an empty one there. You put it in the empty one. So you're just exciting it a little bit of energy. Okay, so let's figure out what orbitals overlap to form bonds. So what I'm going to do is recopy the carbon and the nitrogen right here. Nitrogen, I'll put the N on the side. And we have 1s. And then we have the 3 sp2s. And then we have the leftover 2p. And then for nitrogen, oh, and let's put the electrons in. We had 2 here, 1, 1, 1, and 1. That's for carbon. We already did that. For nitrogen, we also have 2 in the 1s. We have 3 sp2s and a leftover 2p. But our electrons are a little different because we have a lone pair in one of those sp2s. So let's label that one first. This is going to be a lone pair in the sp2 hybrid. Okay, remember, this is our Lewis structure here. Let me draw it. I'm going to draw it because I know it's trigonal on each of these. Okay, so how am I going to get this bond here? I have 3 sp2 hybrids. I'm going to use one of them to overlap with nitrogen. I'm going to use one to overlap with hydrogen and another to overlap with hydrogen. So I will take one of these. This will overlap with the 1s on hydrogen. That takes care of this one. That's going to be sigma sp2 1s. Well, okay, the 2 p's are definitely reserved for the second bond of the double bond. What choice do I have? The only bonds on the carbon, the only orbitals on the carbon are sp2s, right? I'm not going to, 1s I can't use, it's the core. So since you have 2 hydrogens on this carbon, you're going to have to overlap with them. So this is also overlaps with the 1s on hydrogen, and that leaves this one, okay, which will overlap with the nitrogen, because that's the only thing left that's there, right? So I'm going to circle one of these, and so I'll say, okay, these two, well, this is overlap of sp2 on carbon and sp2 on nitrogen. So it's sigma sp2 sp2. And now I have these 2 p's here, and those have to overlap. What is that going to give me? Well, I haven't done that yet. Let me also, this is going to overlap with the hydrogen 1s, right? We have this one other electron here. Sorry about the diagram. So let me just show you with it. So here's our 3 orbitals. These are 3 sp2 hybrids. Here's my hydrogen. So this is my sigma sp2 1s. This is also the same. And now this is a carbon. This is the nitrogen. It also has 3 sp2 hybrids. One of them has a lone pair, and the other overlaps with hydrogen. Okay, here's our sigma bonding. This is our lone pair, which leaves us with this. And remember now, everything is planar. This is planar geometry. We've got our carbon and our nitrogen. And all this sigma stuff is going on in the plane, just like the previous molecule. These are our sp2 hybrids. And then you got this 2p. This has a lone pair. Yeah. So this is your pi 2p, 2p, which is also the second bond of the double bond. And we could draw it nice and simple. Let's keep it simple. I won't ask you to do these diagrams. It's just too much. But I will ask you to do this. Okay, this is like your Lewis structure, but drawn with the right geometry. And then you could label each one of these bonds sigma sp2 1s, sigma sp2 1s, because you know you have this sp2 hybrids on the carbon and on the nitrogen. One of these bonds will be from the sigma, will be from the sp2s overlapping. When sp2s overlap, here's your internuclear axis, and the overlap is on that axis. So that's a sigma bond. Just like these bonds with hydrogen are also on the internuclear axis. So the only thing that's not on the internuclear axis is this pi bond here that's above and below the plane of the molecule. Yes. If you have a double bond, one of them is going to be sigma and one of them is going to be pi. If you have a triple bond, which we haven't got to yet, two of them are going to be pi and one is going to be sigma. There's only one bond that could happen with overlap along that axis. These orbitals don't just go right on top of each other. Like I can't have a second bond with the same region of overlap. That doesn't work that way. This is a lone pair in the sp2. And I forgot the pi. So you could fill in this chart if you want, but I've kind of done this already. Doesn't matter what order you put these in, but we had almost all sigma bonds and just one pi bond. Two of these were sigma sp2 1s between carbon and hydrogen. Then we had a sigma sp2 1s between nitrogen and hydrogen. Then we had a sigma between the nitrogen and the carbon. And then we had a pi, 2p, 2p, also between nitrogen and carbon. So I want to just address one more thing, which I think will be good. And that is, do I need to go through all this work? Do I need to do this every single time, make these diagrams that are confusing? And actually, you don't need to even do that. So, so you can actually simplify this process. But actually, I first have to tell you about the last type of hybrid orbital, which is sp. Okay. So if you have this molecule, this is called acetylene. Okay. You notice that you have two groups of electrons. So you will need to make 2 equivalent hybrids on each carbon. Okay, so that's exactly what we're gonna do. And so this is the last energy diagram. So here's my energy. This is carbon. I first promote an electron, just like we have done before. So that's the same as before. And now I'm going to hybridize. But now I only circle 2 of these because I need 2 equivalent hybrids. And so I will have 2 sp hybrids. And I'll have 2 leftover 2p orbitals. I'll still have my 1s. Okay, and so now what happens in this case is you have these 2 carbons, both carbons have this energy diagram. And what does an sp hybrid look like? Well, here's what they look like. As you imagine, we draw these all kind of the same. But this thing, this is one sp, this is another sp. So I don't want you to confuse this with a p orbital. These are 2 sp hybrids. All right, I think I've run out of time. All right, I'll give you a chance if you haven't seen your test to come and look at it, but you have to give it back because I have to give a makeup to somebody who's got COVID. So if you didn't get a look at it before class, you could come and look at it now.
So the s orbital is like a sphere.
Yeah.
And the p orbital is like domino. So when they overlap, it's the s orbital. So I guess.
We hybridize as a
Oh.
certain number of atoms and make those hybrid orbitals that point in the right direction. Given the geometry and all.
So when you write the SP orbital, it looks just like a p.
No, and it's like one P.
Oh,
And the other one is other S.
okay. So the shape, so the shape of an SP orbital is what?
It's all these shapes of all these orbitals, we don't make much of a distinction between them. Maybe we get fatter and fatter as we go. So here you have most contribution from the P, so these would be more elongated. But
So that, that's.
draws them the same.
SP orbital.
Yes, now it's SP3. This is SP2. Notice they look very much the same, right?
Yeah,
But actually, that's not really true, because there's more part in here, you have a more elongated orbital.
oh, and then it's
This
less part
closer
S.
to the middle. Because
Okay.
it's closer to a P, but they don't have these distinctions in books. This would be a little fatter,
Yeah,
and the nucleus would be more towards the further away from the node. So, and this would be fatter still,
yeah,
but.
okay.
Go ahead.
Are you gonna remember the point, or do you want me to make a note on it? Okay.
You didn't?
No, I got one of them, but then I got one of them.
39.
Where'd you put the S's?
Just the
I see.
Okay. Okay. So I don't have one.
Yeah. I just wanted to divide by 100.
So there would be choice on the final, like, what do you mean? Oh, like topics.
So what,
You'll
I'll tell
probably
you
tell us
exactly,
later.
I'll tell you later. I mean, you will have to do some of this stuff here, because we haven't done it. You
Yeah.
have to do some geometry stuff. We'll have to answer a few of those questions. I think there's like three or four at the beginning of the test. But then I think I have like the next part, I ask you to answer 1 out of 3.
Mm.
And then I have, the next one is like it's like multiple choice kind of short answer, like,
I'm good on
I don't know, 16 out of 25.
So the resonance forms, there's a major, minor, or invalid. I don't remember that, because we're about to have a quiz. Isn't it just, I thought we were just doing what's.
I think invalid is like, if you have like formal charges that are really a lot. Like I think Dr. Longwood said that the one on the test that was
And the valid is like.
-2 and +1 on O, I mean,
Yeah,
that's really gonna be so minor as to be invalid.
Invalid is like when they're all 0, or they're close to 0.
No, invalid means
No, I meant valid.
valid. Invalid is when you have such dramatically bad formal charges that just wouldn't happen.
And then major is.
Major is like a resonance form that's the most stable, will be the most stable.
And
Like
minor,
CO2 with the 2 double bonds on each side are major.
and
With
minor.
the 3 and 1, you have these formal charge differences that are not necessary. Then they be minor.
And minor is good at second place for less stable.
Yeah, like less stable, but not totally out of the, like, ridiculous.
What would equivalent and non-equivalent? I just do like a brain refresher.
Yeah.
We're about to have a quiz.
Okay, so like, CO2.
I can imagine.
All right, CO2, you have 2 and 2, that's fine. Then you have the 3 and 1. That, and then you can have 1 and 3, like those are equivalent. This doesn't matter which sides the bonds are on. But if you have, like we had on the test,
Yeah.
These are all fine. for the most part, but like,
I know.
and so you would have the NCO, right? But this one, that's really terrible for charts. I would almost say that's maybe that. Okay. But-
Like this
and
graph.
This one. This one
okay.
is going to be major because it's a negative one. Oh. And you have the triple bond, you have 2 double bonds, you have a triple one on the end. So that's more minor, and those are not equivalent.
Yeah, that's
Right.
like the.
Because, you know, it's not like CO2, we have the same atom on the side, so you have 3 and 1 and 1 and 3 and 1
I
and
tried.
1 and 3 CO2, those are equivalent. And then minor, because they're not as good as 2 and 2. The formal charges for the 2 and 2 are equal, are all 0 in CO2. But here, it's all different, so this one has 1, 2, 3, 4, 5, 0, 0, negative 1. But if you put the triple bond, the double bond, and the double bond, they have like 1, 2, 3, 4, 5, 6. It's really
Like thinking.
zero. Instead of having like 4 on the lower and on the end. So.
Oh, okay,
This
so I don't feel so bad.
A better major node structure. Whereas the one with the triple bond here is like probably like maybe not even valid, very minor. And what is it, the 2 and 2.
I have to do.
So the more stable
Yeah.
one is gonna be the major one.
And the more stable one, the major ones are a bit more equivalent. I didn't really understand the equivalent part you were doing.
Equivalent, it's like if they have exactly the same energy. So remember on the test, we had NO3 minus. And you had the double bond to the oxygen down here to the side or to the side. All 3 of those are equivalent.
Yeah.
Because none of them,
Like.
Oh, okay.
it's just a matter of positional, it's just positionally different, but who cares? You can hold the molecule a different way, you know?
Yes.
But if you have 2 Lewis structures where you actually like have different formal charges on the atoms, and then they wouldn't be equivalent.
Lowest I can get.
That's nice to know.
Yeah.
Yes, we get 100 on the final.
I mean, I'd like to think positive, but you know,
Yeah.
human error. Are you feeling better? Or like, I don't know.
Yeah. Oh, right, I'm good.
Yeah, that's good. I'm glad.
What's chemistry going on out there? Pressures.
Worried.
Yeah, you go to the crowd, like, that's what they're about.
Wow, I need packing my stuff. Boy, you guys were really tough today. You were tough.
You were tough.
You were tough.
I'm sorry.
I mean, it was like the blank stares and the, oh my God.
It's tough stuff.
It's just for me, I think it's hard to visualize a little bit. So once I get to start visualizing it, we'll start making it more.
Don't worry.
And if you guys are lost, then the back of the classroom is really lost.
Yeah.
I'm just, isn't Orgo this sort of stuff too? Like with shapes?
Yeah, but they're really more about the, just atoms, not like drawing globes and all.
Yeah.
But there's a lot of geometry.
Oh, I signed up for 10 too.
Oh, you did? Okay. Yeah.
Okay, it's the only lecture. And then the lab, I think is the lead.
Yeah, I had to do this Monday once you.
Yeah,
Solidarity,
yeah,
we'll make it through.
we'll be in it.
We'll just have to, like,
Dr. Long.
Exactly.
That's right, Dr. Long.
And then we'll have Dr. Coolidge for that.
Oh, yeah.
Pretty exciting. Can't lose momentum now.
Yeah.
I'm gonna do physiology instead, but no. It can push
Then-
through in the cat.
Summer, I'll take physics 1 and 2.
That's a good idea.
Yeah. The summer session 1, I'll do 1 and 2.
Yep.
2. I keep going back and forth with med school and stuff, but I think I'll just take physics. I feel like it's a lot better, more palatable than anatomy and physiology, and you know, just seems like a.
You want to go to med school and you'll find that stuff palatable. I don't know.
Well, not palatable, but yeah, right. But more like like if I don't have to
Stop
take
this.
A and P,
This is still recording our conversation.
if I don't have to take A and P, then I don't think I will. Since you learned it in school anyway, but
Yeah, the thing is,